Greetings once again, friends. My name is John Gabriel, and this is the New Calculus channel. So, in this video, I'm going to give you a little lesson on the previous two videos. In fact, I'm going to show you exactly how those definitions work with regards to the derivative and the integral in step-by-step format. So, let's begin. Now remember, the geometric identity is this expression here, from which both the derivative and the definite integral are redefined rigorously for the mainstream calculus. So let's begin. Now, in January of 2020, I revealed my historic geometric theorem. This is it here, from which the following, this is the identity from which the theorem comes from. And it was proved that this expression here is the slope of a non-parallel secant line, this expression is the slope of the tangent line, and this is the difference between these two slopes. So the derivative is rigorously defined as the difference in these slopes, in the slope of the secant line and the difference, because it's just this identity with secant slope minus a difference, right? Secant slope minus a difference. But using the same identity, the definite integral is rigorously defined as what you see over here, right? As this expression here, where q of xh is equal to the sum of these. So now I'll explain what those mean very carefully. And in my example, I will use the function, the cubic function. So of course, if we take this cubic function and we expand it, according to my theorem, this will be the derivative and this will be the difference in the slopes, okay? So therefore, the derivative in this case is 3x squared and the difference is 3xh plus h squared. Now notice you don't really need to know h. You don't really need to know q of xh because you can always find it if you know the secant line slope and the derivative, which you do because you get it from this expression here. So all you have to do then is simply say secant line slope minus a derivative will give you the difference in the slopes originally. So let's see how this works for both of them. So now I showed you in one of the previous videos, I showed you this particular applet. And of course, I also showed you in a previous video how the derivative works. So let's first look at the derivative and then we'll look at the integral. Now, so as I told you, the secant line slope is this red line here, and it's simply given by the rise over run, which is that. And then of course, we know that the difference in slopes is given by q of xh, which in this case, as I've shown you earlier on, is simply 3xh plus h squared, okay? So, going back to this one, the tangent line slope, therefore, is given by this value here, which is simply the secant line slope minus the difference in slopes. And notice that the value of n or h does not affect the derivative. So you can move h as much as you like. It doesn't change the value of the derivative, okay? Do you see that? It stays there where it is. The only time it will change is if you move the x value, okay? So if you move it, and then again, you'll see that the derivative remains unchanged. So I've given you links to both these two applets. I'm not going to spend too much time with it. You can ask me to give me a request to download them, and I'll allow you to download them in Google. So what you have to do is send me the request, and I'll respond giving you permission to download it as viewer. Okay, so the definition with the integral is also using this very same identity, okay? And this is how it works. So if we look at this particular applet, which I'll give you a link to as well, all we're doing is we're taking the sum of these and again, these in the case of 3x squared is simply 3xh plus h squared. But remember, if it's difficult to find q of h, that's no problem, because you can simply subtract the derivative from the secant line slope, right? So now, as you can see, and let's show the areas, n equals whatever value doesn't change the total area, okay? It will just simply change the areas given by q of x h expression and the slopes that are calculated in this interval. And I'll explain that in a second. So let's go back there and look. So the orange area basically is calculated as you see over here, and I'll give you a link to this presentation. You can go over it slowly to see that it does give you the exact value, and the same thing with the derivative. And so in terms of the derivative, this expression here gives the difference in slope, but in terms of the integral, it is used to determine the difference in the area between the actual area under the curve and the area given by a fixed number of slopes, as you see over here, okay? This is the area for a fixed number of slopes, and the actual area is simply this plus the difference in the areas. So the slopes and the areas are exact, and there is no need for ill-formed concepts such as infinity, infinitesimals, or the circular rot of limit theory. There are still some cranks out there who are simply denying these facts. They're terribly upset that they've been fooled all these years and that their calculus is in fact bogus. So in this short presentation, I've shown you how the geometric theorem I discovered, not anybody else before me, proves that the mainstream formulation is in fact fraudulent, meaning the results are mostly correct, but the formulation is bogus. And why is it bogus? Because there is no such thing as infinity or infinitesimals, and the rot of limit theory is circular. Oops, I misspelled limit there. Never mind. It's not important. So that's pretty much it for this presentation. And if you have any questions, write them in the comment section. If you write me a snotty comment, I won't even answer you. It will just get deleted. So I'm warning you in advance, don't waste your time, and I will probably block you so that you won't be able to comment again, because I do not have time for fools. And the majority of you are incorrigibly stupid fools, including your professors and all the other morons in mainstream mathematics academia. I'm John Gabriel. This is a New Calculus channel. Until next time, goodbye.